Hello, I welcome you all to this class. In this class, we are going to discuss about the method to improve the performance of a gas turbine cycle, or you can say that method of improving the efficiency of a gas turbine cycle. So if you remember in the last class, of a gas turbine topics, we have discussed about the Brayton cycle, right? And the classification of the gas turbine cycle, that how many types of gas turbine cycle and all those things. So any gas turbine cycle works on the Brayton cycle, which is having four processes. Two are the isentropic compression and expansion, and the heat supplied and heat rejection is at constant pressure, right? And also we generate the efficiency of a Brayton cycle, which is nothing but the 1 minus 1 by Rp to the power gamma minus 1 by gamma. Okay, so now that if you remember, any gas turbine plants mainly three main component, which is compressor, combustion chamber and the turbine, right? Means in compression the air is compressed, and after compression the air is passes to the combustion chamber where the heat is supplied, okay, by keeping pressure constant, and then hot gases will enter into the turbine where the hot gases is expanded, work is produced, and that work, some work we are supplying to the compressor to run the machine, and then remaining work is utilized for the power generation, right? And then the exhaust gases released into the open atmosphere if it is the open cycle, and if it is the closed cycle, by means of the heat exchanger, the gases is that means exhaust gas return back to the compressor. That is the general layout or general working principle of any gas turbine cycle, right? Now, but as an engineer, we should know that what are the method or what are the procedure we can apply by which we can improve the performance of a gas turbine cycle. If you look at the whole mechanism of a gas turbine cycle, right, it means that when the hot means to run the compressor, we means compressor require work input, means we have to supply the work to the compressor. It means that it is a means you can say that there is energy consumption is required, right? Similarly, that when the hot gases, means when the exhaust gases is released, it carries away the heat. That is also another type of losses. It means that if as an engineer, if you can think that how can we reduce the work input in a compressor, okay, and what way we can utilize the hot exhaust gases which is leaving the turbine, right? It means that if you use this exhaust gases to heat the compressor air which is leaving the compressor, right, by means you can reduce the consumption of the fuel supplied, right? So there are the various method only. We have a three method by which you can improve the performance of any gas turbine cycle, right? So before that, I would like to say that in what way you can improve the efficiency of a gas turbine cycle. So if you know the efficiency of any cycle is what, that efficiency of anything, that you can say the output by input. This is just a general discussion. This is the efficiency is output by input. If you look at the output and input relation, it means that the efficiency is directly proportional to the output and inversely proportional to the input. It means that when you increase the output, you can improve the efficiency, but when you decrease the input, you can also improve the efficiency. So on behalf of that, you can say that the performance of any cycle, right, basically if you are learning the gas turbine cycle, so efficiency of a gas turbine cycle can be improved in two ways, either increasing the output or decreasing the input. So let's think that what is the output and what is the input. So output is nothing but the turbine work, right? So as you know that whatever the work is produced by the turbine, that from that work we are supplying the input, means we are giving the work input to the compressor first, and then remaining work is used for the power generation, right? And the second thing means what, input means what, that only one input, that is heat supplied, means that for supply of the heat we require combustion, right? Combustion means what, that fuel you have to consume. Okay, so you need to think that in what way you can reduce or you can minimize the consumption of a fuel in a gas turbine, or how can we improve the work output of a turbine, right? So there are the two methods only, means there are the two way. So for to achieving these two way, we have to learn the three things, right? That is, there are the three method by which we can improve the performance of a gas turbine cycle. The first one is the regeneration. The first one is the regeneration, right? The second one is nothing but we have a intercooling. Second one is the intercooling, and the third one finally we have a reheating. Right? So there are the three methods by which you can improve the performance of a gas turbine cycle, that is regeneration, intercooling and reheating. One by one we will discuss the all three methods. So let's try. First of all, we'll see that you can say the regeneration. Okay, now so first method we are going to learn, which is the regeneration. So make a heading that regeneration means what? That regeneration means again you are generating. So again you are generating means what? That actually if you see the regeneration process, in simply you can say that gas turbine plant, how it's work, that air will enter into the compressor from the surrounding, it compress, reversible adiabatic process, and then the pressure and temperature will rise. So high pressure high temperature gas means air has to pass from the combustion chamber. So in combustion chamber we are supplying the heat, further the temperature will rise. So the hot gases enter into the turbine, it will be expanded. Turbine does the work and we supply the work to the compressor, and then the remaining work is used for the power production. After expansion, the gas, that exhaust gas has to released from the turbine, means it is leaving the turbine. So when the exhaust gases is leaving the turbine, that gas temperature is more than the temperature of the air which is leaving the compressor, right? So it means that it carries more amount of heat. So if you see, there is a kind of losses, there is a huge energy losses, right? So what we think that why don't we reutilize, means regenerate that exhaust gases to heat the air which is leaving the compressor. So when you do this, it means that the fuel supplied or heat supplied in a combustion chamber is less, right? And by which you can improve the performance of a gas turbine cycle, means the thermal efficiency of the cycle can be increased, right? So let us see that you can say the schematic diagram of a regeneration cycle we will discuss first. So first we'll draw the schematic layout of a regeneration cycle, right? And then we will see the working principle, how it can be achieved. Now see, first of all, simply you can say here that this is your compressor, right? This is the compressor, and air will enter into the compressor from the surrounding, it compress, right? It compress, and then this will enter into the combustion chamber, right? After that heat is supplied to the combustion chamber, and then the hot gases, means this will be enter into the turbine further, and in turbine the expansion will takes place, that is reversible adiabatic expansion, right? And then further the work has produced, that few work will supply to the compressor, right, to run the machine, is it or not? And then the remaining gas, means remaining work, is utilized for the power production. And after expansion the gases has to released. So but as we are doing the regeneration, so we don't leave the gases into the open atmosphere, or even we don't send it to the directly to the compressor, right? So we will reutilize that. For reutilization, it means that let's say that this is the exit point of the exhaust gases. So this exhaust gases will come to here, and here we will provide one heat exchanger, right? Here we will provide the heat exchanger, and this is the exit of the gases. So this will be coupled, right? So now you can see that first of all, this is your compressor, this is the turbine, combustion chamber, right, and the direction of flow will be like this. Is it or not? Right? And this is your heat exchanger, right? This is the heat exchanger, and this the shaft is coupled, by which we are transmitting the power to the compressor. So first of all, that air is entered into the compressor, air is into compressor, reversible adiabatic compression takes place, that reaches to the point 2, its pressure and temperature is more than the surrounding, right, and then it will enter into the combustion chamber. This is first case, means first it's happening, right? So it passes through the combustion chamber, and it's here it will be enter into the turbine. So after expansion into turbine, that when the gases is releasing to the leaving the turbine exit, that has more high temperature and high pressure, right, that whose temperature is more than the temperature at 2. Okay, so why don't we reutilize? So we are reutilizing this exhaust gases, and then we are couple them. Here we have a heat exchanger. So when this hot gases, means this exhaust gases, is coming into contact with the air which is coming from the compressor, so now it will be heated. This air will be heated because of this hot gases, so its temperature will further rise, right? When the temperature of this gas which is leaving, which is coming from the compressor and entering into the combustion chamber, now the load on the combustion chamber will be minimized. Means now you have to supply the less amount of heat to the to heat the gases, right? By means you can improve the performance of a gas turbine cycle. So this is 1, 2, this will be your 3, and this is your 4, leaving is 5, that exit from the turbine, and finally you have a exhaust is 6, right? So further it will be enter into the compressor, right? So see that regeneration is what? The regeneration, you can see the efficiency of the Brayton cycle can be increased by utilizing the part of the energy of the exhaust gas from the turbine. So part of the energy of the exhaust gas from the turbine means what? This energy is utilized for reheating the gas which is leaving the compressor. So by doing so, you can improve the thermal efficiency of a gas turbine cycle, right? Now here we will see the effectiveness of a heat exchanger, right? So effectiveness of a heat exchanger, you can say that, make a subheading, that the effectiveness of a heat exchanger, right, of a heat exchanger. So effectiveness of a heat exchanger is what? That it is symbolically epsilon, you can say. Rise in temperature, actual temperature rise of air by maximum possible rise in temperature. So you can say the actual temperature rise of air, actual temperature rise of air over over maximum possible rise temperature. So maximum possible rise in temperature, right? Rise in temperature. So you can say that effectiveness is equal to delta T of actual by delta T of maximum, right? Now, so now if you look at this schematic diagram, so delta T of actual means what? Delta T of actual means rise in temperature, actual rise in temperature from 2 to 3, and maximum possible is what? From T5 to T1, T5 to T2, means this leaving the turbine and the leaving the compressor. So here you can write here itself, that is effectiveness of a heat exchanger is equal to T3 minus T2 by T5 minus T2. Okay, so this is what effectiveness of a heat exchanger. Now if you draw the TS diagram of a regeneration cycle, then how it looks like. So you can say that draw the TS diagram of a what is called TS diagram of a regeneration cycle, right? So this is your temperature and this is your entropy, temperature and entropy, right? So two temperature line is there, that constant, this is constant pressure and this is also constant pressure, right? First of all, what we are doing, that we are compressing the air into the compressor, simply 1 to 2. It is reversible, it is actually isentropic compression, that is ideal. So if I say the reversible means what, 1 to 2 dash, right? Now so it's better that you can see that we are isentropic only, that ideally. So this is 1 to 2, and then further we are, combustion chamber is from here to here, and then this is the expansion. But as it is the regeneration, so regeneration means what, additionally you are adding the heat from where, 2 to 3, right? Now so this heat you can add here, that you can say this is the 1, this is 1, 2, and 2 to 3 you are adding the heat, and then 3 to 4 you are supplying the heat to the combustion chamber. So if you look at that heat supplied, that area of the heat supplied is less, is it or not? That length of the heat supplied is less as compared to the conventional method. So now further, that 4 to 5 you are expansion the gases in the turbine. So this is 4 to 5, right? And further 5 to 6 we are rejecting the heat, right? So if you look at this, so I'll shade these two portion, that is this 2 to 3 and 5 to 6. So these are the shaded portion, right? So shaded portion means what, that means you can say that how much heat you are adding, the same amount of heat you are rejecting. It means that what, but in conventional method the heat supplied is more and the heat rejection is more and heat supplied is less, right? Now so here the heat amount of heat supplied and heat rejection is in equal proportion, right? So this is what you have a TS diagram for the gas turbine cycle, for regeneration cycle. Next method we have that is the intercooling, or that is suppose yes, intercooling, right? Now so next method you can write, that is intercooling. Next is the intercooling. So intercooling is what, that intercooling you already studied in your air compressor topic also, right? That whenever you have to increase the pressure rise, means the you need a delivery pressure required, means you require a more delivery pressure, right? So in that case what you are doing, that we are doing the stages, right? So multi-stage compression is nothing but the intercooling method. So in intercooling method, multi-stage means what, more than one compressor we are using, right? So if means low compressor, high compressor, and so on, so right? So in intercooling we have a two stages is there. Stages by what? The stages by compression. So two compressor we have, we will use here, means we are splitting the work input on a compressor, right? So now, so intercooling you can say the efficiency of a Brayton cycle may increase by the use of a stage compression with intercooling. So you can simply say that, if you want you can write, let's write down the here, the efficiency of Brayton cycle may often, Brayton cycle means gas turbine cycle, right, may often be increased by the use of stage compression, right? By the use of stage compression, and a stage compression is nothing but the intercooling, right? So in intercooling you have a two compressor we use, that is low pressure compressor and high pressure compressor. The purpose is what, that we are trying to split the work input in a compressor, right? But if always remember that when you use the intercooling or reheating, so it won't directly, means it won't give you the better thermal efficiency, right? Until and unless you won't combine that intercooling and reheating method with the regeneration. It means that if you are only if you are the power plant, that gas turbine plant, it works only on the intercooling, right? It means that it won't increase the efficiency of a plant. So for whenever we'll use the intercooling and the reheating, we need to add the regeneration. Means the thermal efficiency can only be improved with the conjunction of the intercooling and the regeneration, as well as the efficiency of a gas turbine cycle can only be improved with the conjunction of the reheating and regeneration. Means with only intercooling and reheating, the efficiency cannot be improved, right, until and unless you won't combine with the regeneration, right. Now, so now that intercooling we'll try to learn with the schematic layout. See here that you have a two compressor. So first I'll draw here a schematic diagram. You can see that is, this is your low compressor, this is the low compressor, low pressure compressor, and this is your high pressure compressor. See, actually the high pressure compressor area should be smaller than the low pressure compressor, right. So it's that there is a mistake to draw the compressor. It will be somewhat more inclined, right. So you just don't mind this one, right. And then this is two compressor we have used. This is your low pressure compressor and this is the high pressure compressor. With this we will add one turbine here itself. So this is your gas turbine, right. Then we'll try to add them, means we will couple them so that we have to supply the work, whatever the work we are getting from the turbine, right. So this is like that, right. Now two combustion chamber we have, first we have to use intercooler here. This is the intercooler and it will be entering, and in between this we have a one combustion chamber, right. And you can see here this is the inlet of the compressor and this is the exit of the compression, right. Now, so here you can say this is the, just hold on, this is the LPC low pressure compressor, HPC high pressure compressor, and turbine CC combustion chamber, and this is the intercooler, right. This is the intercooler. The direction of gas in this manner, like this, like this, like this, like this, right. So first of all, what will happen, that you know already, air will enter into the compressor, that is low pressure compressor, from the surrounding. It compressed, reversible adiabatically, and then it will enter into the intercooler. Why intercooler? Why? Because when you compress the air, its pressure and temperature will rise. So at a high temperature we cannot send the air into the next compressor, right. So we must reduce, means we have to decrease the temperature, and that intercooling means what, that here we have to reject the heat. So when you reject the heat, the temperature will reaches to the initial condition. Initial condition means what, at what temperature the air is entered into the low pressure compressor. So then compressed air will passes through the intercooler. In intercooler we won't disturb the pressure, means the temperature is reduced by keeping pressure constant, okay. Further, the high pressure and low temperature air will enter into the high pressure compressor. So in high pressure temperature, its temperature and pressure further increased. Now it will enter into the combustion chamber where you are supplying the heat, right. So when you supply the heat to the compressed air, which is compressed in the high pressure compressor, further its temperature will rise, and then the heat you are supplying in by keeping pressure constant only, right. So now the hot gases whose pressure and temperature both is maximum, so high pressure high temperature air, and that the hot gas will enter into the turbine. It is strike with the turbine blade, so the blade is a shaft is start spinning and the work has produced. So few work will supply to the compressor to run the machine, and then the remaining work we can get for the power production, right. So this is what the turbine will produce, that is, this is the WT, work done. And then after expansion, the air is leave, means exhaust gas will leave to the turbine, right? So as I told you that if you won't use the regeneration, means whatever the exhaust gas is leaving from the turbine, you should reutilize, right, to heat the compressor. In that way we can improve the performance of a gas turbine cycle. So now these gases will be come back to the air compressor. So here you have a heat exchanger, right, heat exchanger, and then it will be entered into the air compressor right now. So this is what you have a schematic layout of a intercooling. So you can naming this is your, let's say this is 1, it is 2, 3, 4, 5 and 6, right? Now if I draw this intercooling method on the TS diagram, then how it looks like. So let's say that you have a here, right? So where is it? We'll put this one only, right? So this is your temperature on y-axis and the entropy on the x-axis. Okay, so temperature, and this is your entropy, right? Okay. Now, so first of all you have draw the two temperature line that let's say this only we are using. So this is your high pressure line and this is your low pressure line, right? Now stages is there. In stages, where we are doing the stages? In compression. So this side you have a compressor and this is the turbine. Here is the combustion chamber and this is the heat rejection right now. So you know that basics we have already discussed. So let's say we are splitting this compression area, we are splitting into 2 stages right now, so that you can arrange them, that low pressure and high pressure compression. So this is first you can say 1 to 2, that is reversible. This is the isentropic compression. Now I'll tell you that isentropic compression is an ideal and the reversible adiabatic compression in an actual, right? So whatever the Brayton cycle we have discussed, that is the reversible adiabatic compression and expansion I told you, right, which is the actual process. Okay, now so 1 to 2 here, this is wait, this is 1 and let's say this is your 2, right, this is 2. So 1 to 2 is the isentropic compression. First 2 to 3, further here you have a, there it is, 2 to 3 is the intercooling, 2 to 3 is the intercooling, this is your 3, and then 3 to 4 again isentropic compression in the high pressure compressor, and then 4 to 5 you have a 4 to 5 is the combustion, means you are supplying the heat to the combustion chamber, and 5 to 6 is your expansion till here only, sorry it is, right? So this is the 5 to 6 right now. So these 1 to 2 and this is the 3 to 4, right? 1 to 2, 3 to 4 is the reversible adiabatic compression in a low compression, low pressure compressor, and 3 to 4 is the isentropic compression in the high pressure compression, and 5 to 6 is the expansion in a turbine, that is isentropic. Means these whatever I have drawn now, whatever you are seeing here on the screen, this is the ideal process, right? But we need to deal with the actual process right now. So actual is what? That actual is nothing but you have reversible adiabatic compression and reversible adiabatic expansion, right? So here I'll show you the reversible process with this black color of pen, right? So now this is your 1 to 2 dash, 1 to 2 dash. Okay, this is the 1 to 2 dash is the reversible adiabatic compression in a low pressure compressor, means it is the actual, and 3 to 4 dash is the reversible adiabatic compression in a high pressure compressor. Further 5 to 6 dash is the expansion in a turbine, and this is the reversible adiabatic expansion. Okay, now then we have to see the work input of a compressor, work output of a turbine, heat supplied and heat rejection. So let's see that. So we can see here, yes, hold on. Right, so if you see here, that is your what is called intercooling. Work input 2 compressors, so 2 work input means from 1 to 2, and it is the constant adiabatic compression, so mcp T2 minus T1, and again high pressure work is what, from 3 to 4, so mcp T4 minus T3, and turbine work is what, mcp T5 minus T6, and heat supplied is mcp this is T5 minus T4, heat rejection is 6 to 1. Is it or not? That heat, you know, that Cp into dt, that's you already learn the basics of thermodynamics, right? So here I can say that what is called work, compressor work, right? That is WC is your compressor work, right? So what is, let's say that 1 kilogram of air is entered into the compressor, right? So need not to be right, m is equal to 1 we have taken, set. Imagine that m is equal to 1, so it is what, Cp into T2 minus T1 plus, this is your work input in a low pressure compressor, and plus Cp into high pressure compressor is what, T4 minus T3, but we'll take the actual compression. So actual means what, that actual work. So if you see, then you can write T2 dash minus T1 and T4 dash minus T3, right? Actual will learn, so we can say that T2 dash minus T1, and this is your T4 dash minus T3, all right, okay. Then you can say the turbine work. Turbine work is what, that 5 to 6, so Cp T5 minus T6 dash. T5 is the highest temperature throughout the cycle. So that in gas turbine cycle, that air gases which is entering into the temperature turbine, whose temperature is maximum throughout the cycle, that you can remember, right? Then you have a heat supplied. So heat supplied is what, that 5 to 4, so you can say Cp T5 minus T4 dash. I took all actual temperature right now, so there is no ideal condition, means isentropic we are not considering, we are considering the reversible adiabatic compression and expansion, right? So this is what heat rejection in your heat exchanger, that is Cp what, that Cp into you can see T6 minus T6 dash minus T1, and further you can see here, that is intercooler. So intercooler is what, the intercooler is nothing but where the heat is rejected. So here also you can show here, this is also heat rejection and this is also heat rejection. The intercooler purpose is only heat rejecting, right? So two way you are rejecting the heat, that is Cp T6 minus T6 dash plus T6 T1 plus Cp T2 dash minus what, T3. Okay, so this is what that work and heat supplied heat rejection for the intercooling, right? Now next method we will see, which is your reheating. So next you can make a subheading, sorry, that is reheating. Okay, so in see you see that regeneration means what we are reusing the exhaust gases which is leaving the turbine to heat the air which is coming from the compressor, right? In intercooling we are splitting the work input of a compressor, and in reheating what we will do, that in reheating we will provide the stages of turbine, right? Now so the reheating is what, that we can improve the specific work output, right, by splitting the expansion work, right? So in intercooling we are splitting the work input of a compressor, and in reheating we are splitting the expansion work to improve the specific work output of a turbine. So here in reheating we will use the two turbine, one is the low pressure turbine and one is the high pressure turbine. So remember that high pressure turbine, whatever the work is produced by the high pressure turbine, the whole work is will supply to the compressor as a work input. Okay, and then the work which is developed by the low pressure turbine, that work is used for the power generation. Okay, means whatever the, for what purpose you are using the gas turbine, maybe you are using the gas turbine to power the aircraft, right, for the electrical generation, okay, to run the marine, to run the ship, and so on, right. So whatever the work is required, that work you'll use from the low pressure turbine in case of the reheating, right, and whatever the work is produced by the high pressure turbine, the whole work will give to the compressor as a work input, right. And as you know that this method is beneficial only when that you'll use, means you have to combine this reheating method with the regeneration. Okay, it means if you are using the reheating, that won't improve the thermal efficiency of the cycle, right, but once you combine the reheating and the regeneration, the efficiency, the thermal efficiency of the plant or the cycle can be improved, right. So we'll see the improvement, means the schematic layout of a reheating. So let's say that here you can draw. First you have a compressor, so here itself that is the air compressor, right, and then we are using the high pressure turbine, right, and one more turbine we have to use, which is your low pressure turbine. Right now low pressure turbine. See, actually for the high pressure turbine this area should be smaller, and for the low pressure turbine this area should be maximum, right. Now, and in between this we'll use the one combustion chamber. Here you have a one of the combustion chamber, and again we will use the one more combustion chamber, that is here, right. Okay, so now we can combine this cycle. So this is the entrance of the air, that is air into the compressor, and from the atmosphere it will compress and enter into the combustion chamber 1, and then after supplying the heat, that hot gases will enter into the high pressure turbine, right, and then the expansion will take place, work has produced, that work we will supply to the compressor as a work input, right. Now again after expansion the exhaust gases will leave and it enter into the combustion chamber 2. Here also we'll supply the heat, okay, and then the hot gases whose pressure and temperature is high, it will further enter into the low pressure turbine. The expansion will take place and the work has developed, right, the work has developed. So this work is your work output, right, or the low pressure turbine work is also known as the power output, right. So whenever you have to find out the power output of a cycle in a reheating case, so power output of a cycle is nothing but the work developed by the low pressure turbine, that's all. Okay, so after expansion and the work has developed in a low pressure turbine, the exhaust gases will release to the, as we say that we can't release it to the open atmosphere. If you release it to the open atmosphere, there is a huge losses, means this exhaust gas will carry a lot of heat, right. So why won't you waste the huge amount of heat? So instead of wasting the heat, hot gas heat, we will send this heat exhaust gases to the compressor, but here you have to reject the heat by means of the heat exchanger, means you have to cool the air, right. So this is what you have a schematic layout of a reheating cycle. So let's leave the, means let's give the name. This is the compressor, that is C. This is your high pressure turbine, HPT, okay. This is the low pressure turbine, LPT, right. This is the CC1, combustion chamber 1, CC2, and this is the heat exchanger, right. So the direction of flow means gases is in this manner, like this, this is already. Is it or not? No. So let's say this is the one inlet, that is air is enter into the compressor, right? And then it compress, its pressure and temperature will rise, it will passes through the combustion chamber, heat is supplied by keeping pressure constant, right? So further the temperature is raised, so that high pressure high temperature air will enter into the high pressure turbine, it expanded the gases, the spin, because of the spinning of the turbine the work has developed, that work we will supply to the compressor as a work input. Okay, and after expansion the exhaust gases will further enter into the combustion chamber 2. Okay, and here further we are supplying the heat by keeping pressure constant. Okay, and then the high pressure high temperature air, the hot gases will enter into the low pressure turbine, it expanded the gas, yes, the gas is expanded. Okay, and then the work has produced, the whole work is utilized for the power generation. That's why we call it a low pressure turbine, we call it as a power output turbine. Okay, and after producing the work, the exhaust gases will leave the turbine and enter into the heat exchanger. Here the heat has reject at what? At a constant pressure. We are not disturbing the pressure. If you disturb the pressure, the whole game is disturbed, right? So we are rejecting the heat. After rejecting the heat, the temperature will down and the high pressure air further enter into the compressor and the cycle will be repeated. Is it or not? This, if you see, means if you draw this whole mechanism on the TS diagram, then how it looks like. So let's see that. We'll draw the TS diagram. Okay, so this is your temperature and this is your entropy. So temperature and this is the entropy, right? Okay, so as this is the temperature and entropy, so we can say here that this is the high pressure line, right? And this is the low pressure line, right? Now so first of all you have a compression, that is, if I say the isentropic compression means it is ideal. First I'll tell you the ideal only, right? And then stages in turbine, that we are splitting the turbine work in two, that is high pressure turbine and low pressure turbine, right? So let's say this is 1, 2, this is the 3, right? Now that is you are supplying the heat, and 3 to 4, that expansion in the high pressure turbine, and again 4 to 5 you are adding the heat in a combustion chamber, right? And further let's do more, right? Now so further 5 to 6, further it is expansion in a low pressure turbine, and then it will send back to the compressor, right? So now this is what you have shown. This is the ideal process, means isentropic compression and expansion I shown you, right? Now if it is the actual process, then how it looks like. So for actual case it will be something like that. So this will be 1 to 2 dash, right? 3 to 4 dash, yes, this is 4, this will be 4 dash, and 5 to 6, and this will be the 6 dash, right? It means that 1 to 2 dash we call it as a reversible adiabatic compression, 3 to 4 dash is the reversible adiabatic expansion in a high pressure turbine, and 5 to 6 dash we call it as a reversible adiabatic expansion in a low pressure turbine. And then arrow you can show like this, that is, this is the compression, the heat is supplied here, expansion in a high pressure turbine, expansion in a low pressure turbine, and the heat is rejected in 6 to 1, right? Now you can see the work, turbine work, that is output work, and the input work. So 2 turbine, and let's say that 1 kilogram of air is entered into the compressor, right? So heat turbine work is what? Turbine work is nothing but in a high pressure turbine plus low pressure turbine. Compressor work is 2 to 1, and the heat supplied is 2 to 3 and 4 to 5. Heat rejection is 6 to 1, right? Now so you can write here itself, or you can change the page. Yes, now now. So now you can say the here turbine work is equal to what? Turbine work is nothing but the Cp into T3 minus T2. Just wait. This is 2, 3, 4, 5 and 6 right now. So means what? That is 1 to 2 dash, 2 dash to 3, and 3 to 4, 4 dash, 4 dash to 5, and 5 to 6 dash. These are the actuals, right? So you can say sorry, this will be cut this, very sorry, that turbine work is equal to Cp, right? Work in low pressure turbine, high pressure turbine, and work low pressure turbine. So high pressure turbine is what? T3 minus T4 dash plus Cp T5 minus T5 not T5 dash, no, T5 only, yes, T5 minus T6 dash, right? And then compressor work is what? That simply Cp T2 dash minus T1. Actual temperature we are taking, right? Heat supplied where? That heat you are supplying in combustion chamber 1, that is Cp T3 minus T2 dash, all right, plus Cp where? T4 dash T5 minus T4 dash, right? And the heat rejection is Cp, that is T6 dash minus T1. I'll show you that Cp T3 minus T4 plus T5 minus T6, that is T3 minus T4, T5 minus T6. Work is what? T2 minus T1. Heat supply 3 to 4 and plus 5 to 4, and 6 to 1 is the heat rejection. So this is how we can do the calculation for the regeneration. So these are the three methods which we have learned today, that regeneration, reheating, and intercooling. So regeneration is nothing but the reutilization of the exhaust gases which is leaving the compressor, right? And by doing this you can reduce the consumption of the fuel, right? And intercooling is what? That method of splitting the compressor work in two stages, that like by using the high pressure compressor and the low pressure compressor. Further, then reheating, that is, it is the method of splitting the expansion work in a turbine, right, in a two stages by using the high pressure turbine and low pressure turbine. So high pressure turbine is used to run the compressor, means work is used to run the compressor, and the low pressure turbine is responsible for the power output. And so these methods, means by intercooling and reheating, you can get you can improve the thermal efficiency of a cycle only when we combine this procedure or this method with the regeneration. Without conjunction of the regeneration, the intercooling and reheating method is not much efficient. Okay, so this is all about the today class. In the next video we will discuss some problems related to these methods. Thank you.